Welcome to Unit 7, Cartesian Vectors, Lesson 1, using what we know about geometric vectors. So that was last unit. We're going to explore Cartesian vectors. So today, again, we're going to look at last unit and we're going to compare it to this unit to start with. What is a position vector? A position vector is a Cartesian vector. What's a Cartesian vector, Mr. Wills? It's anything that is on the Cartesian plane. So this guy right here, this vector AB, is a Cartesian vector because it's on a Cartesian plane where its tail, this is important, its tail is at the origin. So right now this guy, this tail, which is point A, is not at the origin, so this is not a position vector. So what do we do here? To make it a position vector, we just take our vector, again, same magnitude and direction, we're going to drag it so that its tail's at the origin. So there we go. So we know that vector AB is defined by where the tip of it is. The tip is right there. So we can say vector AB is equal to the tip, so that would be 5, -6. So that's what it looks like geometrically. Algebraically, this is what we're really going to be focusing on, the algebra. We're going to use this formula here. Notice how it's very, very similar to the slope pattern, or slope formula, x2 minus x1, bracket, or comma, y2 minus y1. So here my x1 is right here, my y1, x2, y2. So here I know vector AB is going to be equal to 3 minus -2, comma, -1 minus 5. And so if I do this quickly, we can see that AB is equal to 5, -6. So you can see that geometrically we did it here, and then algebraically, which is what we're really focusing on, there's our formula for converting any Cartesian vector to a position vector. Next, we're going to talk about magnitude. Magnitude given 2 points in the tip and tail. We want to find its magnitude. So for instance, here again, vector AB, same vector as before. What I want to do here is I want to find the magnitude of AB. So what I'm going to actually do here is drop a perpendicular, a vertical, and a horizontal to make a radical triangle. Why would I do this? I'm doing this so that I can use Pythagorean theorem here to figure out the magnitude of this. I know the vertical side squared plus the horizontal side squared is equal to the diagonal side squared, which is the magnitude of that vector. So here if I count them, 1, 2, 3, 4, 5, 6, so the side is 6. 1, 2, 3, 4, 5, that's 5. So I know the magnitude of AB is equal to 5 squared plus 6 squared, which is equal to 25 plus 36, so the square root of 61. That is geometrically. If we do this algebraically, again, we're focusing on the algebra here, we can look at this formula here, and if you notice, this formula is actually the formula from grade 10 math. It's the distance formula. So we're just going to pull that one out of our hat. So what do I have here? I'm going to have the magnitude of AB is equal to x2 minus x1. We defined x2 and x1 and y2 and y1 before. So it's going to be 3 minus -2 squared plus -1 minus 5 squared. So here I'm going to have the square root of 5 squared plus -6 squared, which is going to be 25 plus 36, so the square root of 61. So geometrically and algebraically, there we go. Continuing on, here we go for the position vector. So if I want to find the magnitude of the position vector, so again, notice the tail is at the origin, that's what we want. We want the magnitude of V, so again, we're going to pull the same thing geometrically. We're going to drop a vertical and horizontal. We are going to measure the vertical and horizontal side length. So this is 2, this is 3. Notice how, again, very conveniently, that's actually the position vector. So to get this, again, it would be 2 squared plus 3 squared equals magnitude of v squared. So I know that v squared, the magnitude of v is equal to 2 squared plus 3 squared, which is 4 plus 9, which is square root of 13. So using Pythagorean theorem, I got that. And again, here's the formula, the algebraic formula. This is the formula I'm going to be using. So to do this, magnitude of v is equal to the square root of 2 squared plus 3 squared. And so again, 4 plus 9 is square root of 13. So we can do it that looking at our diagram there. Here's our diagram geometry. Next example, vector addition. So here we go. Due to the confusion that comes with multiple vectors, in this page we'll no longer use the notation x1, y1, x2, y2. We are simply going to use this notation here. U is equal to u1, u2, and v is equal to v1, v2. So this is how we're going to solve it algebraically, but let's look at geometrically. Given vector u, which is 1, 3, so here's our vector u right here, and v, which is 4, negative 1, there's our position vector v. Find u plus v. So geometrically, going from last unit, what I can do is put these two vectors tip to tail. So I'm going to move my vector v so that it is at the tip of vector u, and then once I do that, my resultant will be this red vector here. So I can see u plus v is actually equal to the position vector 5, 2. So u plus v is equal to 5, 2. Now, how do we do this algebraically? To do this algebraically, what we do is we label our points. So again, I had this one, I had u. So I know u is equal to 1, 3, so this would be u1, this is u2, and I know v is equal to 4, negative 1, so this is v1, v2, so I know u plus v is equal to u1 plus v1, so it's going to be 1 plus 4, comma, u2 plus v2, so it's going to be 3 plus negative 1. So here I get 5, 2. So the same as I would geometrically, just by adding up the first coordinates and second coordinates, and I get that position vector there. Continuing on, decomposition of a vector into its rectangular components to given a position vector. So here I've got uv right here. So here's my position vector uv right in terms of the vectors I and j. Well, what are I and j, Mr. Wells? I and j are simply I is 1, 0, the position vector 1, 0. So it's a horizontal unit vector. Unit vector means it has a magnitude of 1, and then j is 0, 1, so it's a vertical unit vector. So what would I do here? I'm going to see how many vector i's I have here. So here I have 2 vector i's going this way. Again, I can move this so it's over there. And then let's see how many j's I have here. So 1 vector j's, 2, 3, 4, and 5. So here I know that if I want to write it in terms of I and j, I've got 2 vector i's and 5 vector j's. These are all positive because they're always going to the right or up. So I can write this as vector u is equal to 2i plus 5 vector j. And this a and this b really are u1, u2. To do a position vector, writing in terms of its horizontal vertical component, so here, this vector here, this red vector here would just be, alright, so this vector here would be 2, 0. This vector blue, this blue vector here would be, oops, if I move this over here, it would be the vector, position vector 0, 5. So I can write u as 2, 0, that's its horizontal component, plus its vertical component, which should be 0, 5. There we go. And then finally, here's the last one. I want to do, given a magnitude of vector as an angle of the horizontal, so here I have this. Again, geometric vectors, I got the force of 200 newtons at 25 degrees of angle of inclination. That means to the horizontal, above the horizontal. Express the force as a position vector. So what I'm going to do here is I know that this is 200 newtons. I've got an angle here, and what I want is the horizontal force, or sorry, the vertical force and the horizontal force. And so I want to write like this. I want to write my overall force is equal to the, we'll go, because x comes first, the horizontal force, comma, the vertical force. It always goes horizontal first, then vertical, just like x and y. X is on the horizontal axis, y is on the vertical axis. So here, I can, well, and I know that the magnitude, going back to last unit, of h is equal to 200 cos of 25, and I know the magnitude of v, again going back to last unit, is 200 sine 25. So what does that mean? That means that vector f is actually equal to 200 cos 25 in my calculator is 181.3. I'm going to have here 181.3, comma, and then 200 sine 25 is equal to 84.5. And again, notice I could have done this just using the algebraic formula right there.